Hello, QST readers and ham radio operators around the world. I'm Dave Kassler, amateur radio call sign KE0OG, and I write the Ask Dave column every month in QST. And I also make a short video to go with each. And this is the accompanying video for the December issue of QST and Ask Dave. And the question I want to expand a little bit on came from Jim Kelly, N8YDM. Who asked the question about whether a balun should be a DC short, and the answer is yes. I thought what I would do today, instead of concentrating just on baluns or on uns or something like that, is just talk about transformers and how they work. There are two kinds of baluns, choke baluns, and then there are the transformer baluns. The transformer baluns are very common. For example, if you have an end-fed half-wave antenna, you have a 49-to-1 balun or a 64-to-1 balun that feeds into the thing. And it will look like a DC short to ground, but it isn't. So we'll show you it is a DC, but not at RF. Let's take a look at a drawing I've got here. This right here is the schematic diagram for a transformer. Now, the thing about this is that it's actually very much like what it represents. This is a coil, and this is a coil. This coil you usually read this way. This is the primary winding, and this is the secondary. It is possible to put another winding over here and call this the tertiary, or it's usually called an additional winding or something like that. For example, the secondary might feed into a high voltage power supply, whereas this one right here supplies the filament current. But let's not make matters too complex right out of the bat. The first thing we want to look at are the elements here. We have, this is the core. It's a piece of metal or something magnetic. Now, in power supply transformers, these are actually leaves of metal. They're usually in an E form like this, and then they've got opposite ones like this, and they're interleaved together, and the coils are wound in the open spaces here. And the reason that they are sliced into metal pieces is because if they made it solid metal, the so-called eddy currents would make the transformer very inefficient. Now at RF, the core of the transformer is usually a toroid of some kind. A toroid means a donut. Okay, and the windings go like this, you know, in and out and around. The advantage of this type of winding is that most of the magnetic field is within the toroid. The toroid can be made of a variety of materials, such as powdered iron that's got some sort of a coating on it, so you can kind of squish it together and it'll make something that holds together, but it still insulates each piece from the other. It can also be made of rare earths, all different kinds of things. Now, I want you to look at the primary here. It's a coil, okay? So if I were to take a battery, okay, and attach it to an ammeter here, attach it like that, you would see direct current flow. Now, at the very start of the flow of the direct current, the magnetism in this coil would spike. The change in it would cause a change in current over here. So this goes like this. You get a spike, and then the current, and what you would see over here would be just a little spike, because when it becomes steady, it will not induce a magnetic field over here. Okay? It is the change in a magnetic field that will induce a change in the electrical current in the secondary. Now, this works the same at all frequencies, but the sizes get changed as you go. Let's take our battery away. We don't need that. By the way, if you do put DC through a transformer, there's a good chance you'll burn the winding out, and you don't want to do that. Now, let's put over here an oscillator of some kind, okay? And this is going to induce a magnetic field in here, and then it's going to change back in the other direction, and let's just say it's in the form of a sine wave, okay? So we move the magnetic field in one way, and then over here we move the magnetic field the other way. This creates a changing magnetic field, which is going to induce an AC current, and the phase is going to be slightly different, but I'm just going to draw it this way, in the secondary. Okay, so you put AC in, you get AC out. Now, a couple little things to think about right here. First of all, the core material is very dependent on the frequency. If you're doing it at 60 hertz, namely household utility current, 50 hertz in Europe, and in lots of other places in the world, and I think there's still a couple places in the world where it's 25 hertz, but 60 is the standard in the US, 50 hertz is the standard in Europe. Now it's interesting, the lower the frequency, the bigger the core's got to be, okay? And so you'll find that to make very efficient transformers, what they will do is use a much higher frequency. Aircraft usually use, if they've got AC on them, 400 hertz. They can make their transformers much smaller, like half the size or so, and save the weight, and use the weight to carry cargo or passengers, okay? Now, this is constantly changing, okay? And what this sees right here is it sees a pushback from the inductor, especially this inductor over here. If this inductor isn't connected to anything, then its current isn't going to matter. But it can be connected to some kind of a load, which we'll just mark as some sort of a resistor over here. So here's the great secret to transformers. Let's suppose that this right here is, say, 1 megahertz. So what's going to come out is 1 megahertz, because these two follow each other. Whatever the voltage is here, now we've got a load over here, so there's going to be current flowing. Let's say this is 10 volts, and it is at 10 amps. It's 100 watts there, okay? 10 volts, 10 amps. But let's say that the turns ratio, this may be some number like, well, if we're using 1 megahertz, it may be something like 5. And this over here is 10, okay? Then what you're going to have out here is 20 volts at 5 amps. In other words, the voltage is multiplied by the turns ratio, which here is 2 to 1 over on this side, okay? So this gives you less current, more voltage. So if you need high voltage, like to run a tube or something like that, you can do this. Now note here that the current is changed by the inverse of this. So if this goes up by 2, this comes down by 2. This is 100 watts, and this is 100 watts. Now, you may say, isn't there some loss in here? Well, yes, there is. You heat the core. So this is why you want to make your transformer as best you can, so that you get the maximum transfer. You select your core material very carefully to get the maximum transfer. If you're building a kit, somebody's already made that selection for you. Now, what is the impedance over here? The impedance, which I'm just going to put in parentheses R, because that's what we think of it as. But impedance, the difference between a resistance and an impedance is the impedance includes a phase angle, but we're not going to worry about that. The impedance is the voltage, E, divided by the current, which is I, in ham radio parlance, okay? So this comes from Ohm's law, that E equals IR, and you just pull the E. So the impedance is the voltage divided by the current. Well, let's see what we've got here. We've got 10 volts in amps, okay? So we've got 10 divided by 10. The impedance right here is 1 ohm, okay? 1 ohm. Now, I'm just making up cases here. But now notice here that the impedance on this side is 20 over 5, which equals 4 ohms. 1 ohm to 4 ohms. So we have changed the impedance on this side. And note that that 4 is the turns ratio squared. That's the important thing to note here. The impedance change is the square of the turns ratio. The voltage is the turns ratio times the input voltage over here. So if we want to make an RF transformer of some sort, and let's suppose that we have something with a few windings over here and a nice toroid core that everything is wound around. We have like 10 turns here, and we have like 20 turns here, okay? So let's put this in and set this up so that the current, 50 volts at 1 amp. The impedance over here is 50 ohms, which we're used to in ham radio. Now our turns ratio again is 2 to 1. So this is now going to be 100 volts at 0.5 amps. This is 50. This is 50 in terms of power. The power is 50 watts on either side. So we're not changing the power. This is important. We're not changing the power, but we will change the impedance. The impedance here, it's the square of the turns ratio. So if you take 100 and divide it by 0.5, you get 200 over here. And this becomes the impedance. It's expressed in ohms. Yes, there's a phase angle, but we're not worried about that at all. So the ratio right here is not 2 to 1. It's 4 to 1 for the impedance. This is how we can take a 50 ohm circuit and convert it to an impedance that we might want to use for an antenna, for example. This right here, it's balanced on this side, balanced on this side. So bow, we'll just call it a balun, is a 4 to 1 balun. So we take this 50 and convert it to 200. Now there are a number of cases where you might want to use that. If you're going to feed an off-center fed dipole, we know at a dipole, here we'll just make that the middle part, the impedance at the center is like 30 to 70 ohms, depending on the height above ground and the wavelength. Okay, so we feed this with our 50 ohm coax. But if we want to feed it, say, here, we may find that this impedance is 200 ohms. Okay, and it keeps going up as you get closer to the end. So this is where we would put a 4 to 1 balun in to take our 50 ohm line and convert that to 200 ohms. Now if you're going to end feed it, a common balun is 49 to 1, which actually means a 7 to 1 turns ratio. Remember, we take this and square it. 1 times 1 is 1. 7 times 7 is 49. 49 to 1, okay? Now, if that means if we have 50 ohms over here, we will have 2,500 minus 50 to get the 49 is 2450 ohms, okay? Your printed edition of QST may have a wrong answer there, may have 2250. We fix that in the online edition, okay? So this is how you get the high impedance to feed at the end. And so you get your turns ratio of whatever this is. 3 is a common value. 21 is a common value over here for the turns on a nice toroid. And very often this is connected to this, and this is connected to ground. So this is actually an unbalanced on both sides. But people call them balance even when they shouldn't. Okay? Now, the question that he had was he used an ohmmeter to measure the impedance here and found that this was a direct short. Well, it is at DC. You're going right through a coil. And remember, an unchanging current will not generate a magnetic field over here. It'll create a magnetic field here, but it takes a changing magnetic field to induce a current over here. So when you do the AC, now this sees the load impedance, okay? So this looks like 50 ohms at RF, where it's 0 ohms at DC, okay? Now, This is a hard concept for some people to understand, but when you put an AC or RF current through a coil, it generates what's called a back EMF, okay, which is like pushback. A coil does not want the amount of current flowing through it to change, but you're changing it all the time. So this thing is reacting every time you change the current, creating a backfeed on the thing, and that's why that's not 0 volts. Now, if you couple that over into here, then you couple in the load impedance over here, and you have a very nice little circuit. So this just gives you a little quick overview of how transformers work. And the same basic idea works for all transformers at all frequencies. You can't have a transformer at DC. Now you said, well, wait a minute, we've got DC to DC converters. Yes, those operate under a different principle. First, you have to convert it to AC, pass it through the transformer to change your voltage to whatever you want, and then rectify that back to DC. Now, if you switch that transformer at a high enough frequency, it can be quite small. This is why DC to DC converters, or like your power supply for your station, work. They're operating at around 50 kilohertz or so, and that allows the transformer to be quite small because of the high frequency. Now you ask, well, wait a minute, isn't there a limit on this? The answer is yes. If you're doing microwave circuit layout on a circuit board, you may need a certain amount of inductance, and it might end up being a half a turn, and then it will continue on in the other direction. So you need to do funny little things like this to make it work. So there you have it. That's how a transformer works. Please become a member of the ARRL and support the fine work that it does. I just attended the HamCon Colorado, which was the Rocky Mountain Division ARRL convention, and had a great time there. Lots of people spoke and gave forums and so on. I was the breakfast speaker and also did a forum on Whisper. So there you have it. Until we next meet, 73.